The internet is going crazy over this fraction. If you look at its decimal representation, every 24-bit string has a Fibonacci number in order. Why is this fraction generating the Fibonacci numbers? What's going on? And by Fibonacci number, we mean a sequence described by Pingala more than 1,000 years before. To answer this mystery, we'll look at a seemingly unrelated question. What is 1 divided by the polynomial 1 minus x squared? We can do this by long division. Our first quotient will be 1, and then we'll subtract out, and we'll be left with the result x plus x squared. This gives our next quotient of x, which we then subtract out. We have 2x squared plus x cubed. So our next term will be plus 2x squared. Subtracting that out, we have 3x cubed plus 2x to the fourth. So our next term will be plus 3x to the cubed to eliminate the 3x cubed. When we do that subtraction, we end up with 5x to the fourth plus 3x to the fifth. So our next term will be 5x to the fourth. And now we're seeing a pattern in the coefficients of this polynomial. If we write f to the n as the nth Fibonacci term, we have 1 divided by this polynomial will be f1 plus x times f of 2 plus x cubed times f of 3 plus x cubed times f of 4, and so on. Each new power of x will be associated with the next term of the Fibonacci sequence. So how is this going to help us solve the mystery? Well, let's use a simple and special value for x. Let's use x is equal to 10 to the power of negative 24. Or this is 1 divided by 10 to the power 24. And what's interesting is you can use different values of x here. So in our problem, we had 24-bit strings that were the Fibonacci numbers. But you can experiment on your own and try and figure out different values of x. When you substitute this value in, you end up with this quotient, which we'll then simplify to this following fraction. If you calculate what's in the denominator, you end up with that crazy number with all the 9s and an 8 in the middle. And the only difference between this number and what we want is we need to divide this by 10 to the power of 48, which is x squared with our value of x. So then we end up with the exact fraction that we started out with, that crazy fraction. And we know from what we just derived, this will be equal to what this series of powers of x associated with Fibonacci numbers shifted over by 2 powers of x. In other words, we figured out that this crazy fraction is equal to the following infinite series. If we write this using x is equal to 10 to the power of negative 24, we end up with the following expression. So this means every 24 terms, we're going to get a new Fibonacci number. And that's exactly what we had at the beginning. So that's why we end up with this crazy representation. And one thing I'm going to leave you with is obviously this is a rational number. So once you get to the point where all 24 numbers, all 24 bits are filled up, it actually breaks the pattern, and eventually this is going to repeat. You're not going to keep getting the Fibonacci numbers infinitely many times. Because this is a rational number, the decimal is going to repeat. But you can try different values of x, and that's why this formula comes up. I hope you liked this video. Please subscribe to my channel. I make videos on math and game theory. You can catch me on my blog, Mind Your Decisions, which you can follow on Facebook, Google+, and Patreon. You can also catch me at Presh Talwalkar on social media. And if you like this video, please check out my books. There's links in the video description. Thanks for watching.